Hi, my name is Melanie Wille, and in this video I introduce our paper, Are All Marine Species Created Equal? Performance Disparities in Underwater Object Detection. This is work completed in collaboration with Dr. Tobias Fischer and Dr. Scarlett Rain at the QUT Center for Robotics. It is out of question that our oceans are incredibly important to us and all life on Earth. They cover more than 70% of the planet, provide oxygen, regulate climate, and offer valuable food and energy resources. However, humans still threaten them through overfishing, pollution, and rising sea temperatures because of climate change. Underwater object detection can be a tool when trying to fix that, as it is crucial to operate autonomous underwater vehicles, to enable robot picking, for example for aquacultures or garbage removal, and to evaluate collected data for more sustainable resource management and marine monitoring. It achieves all of that by combining classification, that is identifying the type of an object, and localization, which is determining an object's position. Therefore, object detection can tell us the what and where for multiple different objects in one image or video. There are three main steps when performing object detection. First, distinguishing an object of interest from the background, then localizing its exact position with a bounding box, and lastly, classifying it by assigning it to one of the predefined classes. Performing object detection underwater is particularly challenging though. The images are usually blurry with tricky light conditions, low contrast, blue-greenish color, and overall just poor image quality that makes it very hard for the human eye to find marine animals, especially because they are also often very small, clustered together, and seem similar to each other and the background. On top of that, in-field use is limited by the robot resources on board, and the number of annotated, publicly available datasets for training models is quite low, because labeling these images requires an expert to correctly identify all the marine targets. Some of them seem subjectively more difficult to spot than others, and our extensive literature review has shown that this is not only the case from a human perspective, but also applies to detection performance. A good example is the scallop class in the Detecting Underwater Objects or DUO dataset. It contains more than 6,600 training and 1,100 test images with 4 classes, whose representation is very imbalanced. Equinus represents around 67% of objects, while scallops, shown by that little bit of yellow, make up only 2%. We noticed that across a range of studies benchmarking on DUO, scallops always perform the worst by far, no matter what architecture. We wanted to understand why that is, but most of the works didn't address the performance gap at all, and the few that did gave the small number of training samples for scallops as only reason, without considering or testing any other factors. To the best of our knowledge, there is no systematic analysis to date regarding where persistent performance gaps between classes come from, which is why we present the first. We investigate the influence of data quantity and class distribution versus inherent visual characteristics of the target objects to explain the underperformance. This is crucial because we can address the first when collecting data, but the second only on algorithmic level. To validate our findings, we repeat our analysis on RUOD 4C, which is a 4-class subset of the Rethinking General Underwater Object Detection dataset. It does not have the same class imbalance as DUO, but still shows a scallop underperformance. We designed a 2-stage experimental framework that breaks down the object detection process into the localization and classification stages. Our localization study examines how well targets can be distinguished from the background and how well accurate bounding boxes are placed by using single class versions of the datasets. We completely ignore classifying the objects between the different classes because this is analyzed separately in our classification study. Here, we use single object versions of the datasets to simulate the selected image areas that are passed to the classifier. In both studies, we conduct experiments on the original imbalanced data, on balanced sets with the same number of training instances, and on gradually decreasing data quantity. We employ the YOLO11 object detection model pre-trained on COCO as localizer and ResNet 18 pre-trained on ImageNet as classifier for our main results reported. But we also repeated our experiments with SSD, MobileNet, and Vision Transformer for architectural ablations that confirm our findings. All models are fine-tuned on our custom data for 30 epochs, and we use both standard evaluation metrics, including MAP, precision, recall, and F1 score, as well as special evaluation tools like TIDE. Most prior works don't use extensive error evaluation, but only report aggregate metrics like average precision that hide detection patterns. In our analysis, we utilize the TIDE toolkit, which categorizes errors into 6 categories and calculates the loss in AP caused by a specific type. Fully missed objects and localization errors when the bounding box is too far off are the ones we gained the most insights from when evaluating our localization study. The localization experiments on the original single-class datasets clearly show the performance gaps that previous object detection works have reported in both MAP and recall. Performance is really high for Echinus and Starfish and still good for Holothurian, but the scallop class is notably lower and in DUO only reaches around half of the other classes MAP and even less in recall. Therefore, we highlight that class-specific disparities are highly evident in the localization stage. While these results could still be due to the low number of scallop examples, like the previous papers claim, the MAP and recall results in the balanced setup are very similar. The bars indicating the balanced performance usually have the same relative relation as the lines above them, which represent the results of the original distribution, and the gaps remain evident. Therefore, we revealed that class-specific disparities persist in balanced conditions, which means that data quantity cannot be the only explanation for the performance differences, but species-specific intrinsic features must have an influence. To further analyze the influence of training data quantity, we gradually reduce the number of training samples. Although performance generally declines across all classes, scallops and Holothurian show a stronger rate of performance decrease. We therefore conclude that classes depend on data quantity differently. Taking starfish samples away doesn't affect them much, whereas scallops strongly rely on certain training examples, which indicates that the model cannot learn characteristic scallop features as easily. We also find that the generally most common error is completely missing an object in any class. There are basically no localization errors at all, and the decreasing gap between the MAP values with higher threshold shows that bounding boxes are placed similarly well for every class. Therefore, we identify foreground-background distinction as the main bottleneck. The first part of localization remains the most challenging step, also when considering the full detection process, as the results on the original single object crops in our classification study show extremely high precision, recall, and F1 score, consistently over 90% for all classes. Although scallops always remain the worst class, the performance gaps are much smaller in the classification stage. When we balance the training data, we notice changes in the DUO dataset. The scallop recall improves to be the second best, but precision drops extremely because scallops get so much more attention in training than before. Based on the F1 score, scallops have even performed better overall as a minority class in the original imbalanced data. Therefore, a key insight from our classification study is a precision recall trade-off for minority classes, depending on the class distribution. On one hand, higher precision with imbalanced data, which is suitable for commercial applications, for example, when we specifically want to harvest a certain species and this species only, without wrongly interfering with a different animal. But on the other hand, higher recall with balanced data, which is needed for conservation and marine monitoring to never miss the occurrence of an invasive species. This pattern stays consistent, also when reducing the balanced data quantity, even though scallops do have the largest fluctuations. When we only reduce the data for one class at a time, from the original datasets, scallops are affected strongly by changes in any class, while the other classes are more robust or change mainly when their own data is affected. Therefore, our last conclusion, scallops have less distinctive features, which is why they are a sensitive class that relies on data from other classes to learn what scallops are not. Overall, our findings bridge a current gap in the literature by providing the first systematic analysis of class-specific performance differences and breaking down object detection into localization and classification. We prove that intrinsic species-specific features play a crucial role and highlight that the localization stage should be focused on more to mitigate class disparities, especially for visually less distinctive species like scallops. We reveal fundamental precision recall trade-offs in classification, point out interclass dependencies, and offer practical recommendations depending on application needs. We conclude that performance is generally better with more training data, but targeted algorithmic improvements are necessary because a species' visual characteristics inherently influence their detectability. Based on our work, future works could focus on improving localization over classification, in particular foreground-background distinction, integrate additional sensing, develop standardized per-class evaluation, or try quantifying the visual difficulty of a species to guide data collection and annotation. In the end, our paper offers fundamental findings that provide guidance for targeted solutions and improvements in underwater object detection. Thank you for watching our video.